Good morning, everyone. Happy Tuesday.
Good morning.
Are we ready for some cool learning
Good
activity? Anyone have any questions before we get started?
Yes, actually, I do. The Constellation Quiz, what exactly does that entail? Is it like the other tests, or is it?
No, I meant to erase that off of the syllabus. We used to do that when we had access to the planetarium, or if we didn't have access to the planetarium, we'd do it outside in a group pointing out constellations. The only thing that'll bear any resemblance to that is you're doing labs, and there may be, on occasion, a test question that will have a picture or drawing of a particular constellation, and I might ask you to identify it.
Okay. One more question.
Sorry, Matthew. One more thing. Does looking it up count?
Does what? Looking it up? No. This would be a test and respondus. So it'd be something where you're not allowed to look it up. Go ahead, Matthew.
So we're not doing the Constellation Quiz?
No, and that's something y'all should shoot for, just as people that either like astronomy or are interested in continuing studying astronomy. I would say you try to go out and learn as many constellations as possible, just for the fun of it and the knowledge and the cool mythology and stuff like that. So I've always made that a goal of my course. This under quarantine, though, all I can do is hope that you guys are doing the labs and learning some constellations from those experiences.
Okay, now one more thing. It's a quick story. Y'all are gonna love it.
All right.
So the moon lab, right?
Mm-hmm.
I'm still trying to do it. I'm not able to get a lot of the moons down, because of how cloudy it is, and sometimes the light pollution gets in the way. So for the past 3 days, it's been cloudy, and I've just been struggling, right? And I had this brilliant idea. Hey, I have a friend that lives in Pennsylvania. What if I call him?
That's cool. Just give me the city that you're in, so I roughly know what's going on. And you'll have to use his time if he's past the timeline, which I think all of only a small part of Pennsylvania, if any, is out of a different time zone than us. And I don't think any of it is actually. Yeah. So you should
hold on. It gets even better. I call him up. I ask him what the moon looks like, and he tells me I cannot see a goddamn thing.
I got bad news. Next week I'm seeing more and more rain and cloudy, like for real.
Yeah, y'all guys are too fixated on the weather, man. Just chill out.
Sir,
observe the moon when you can. Every day, look it up, see what time it rises and sets, and then try to go out at some time during that period and see if you can get it.
Sir.
Yes. Do you mind?
No, that's me.
Wait, I'll let him say his question.
Go ahead, Matthew. Excuse me, Tyler. Tyler, do you have another question, buddy?
No, it's Heath.
I'm getting confused here, sir. I thought Tyler was talking to you in the
I messed up everything. I'll get you next, Jamon. Go ahead, Heath.
So, sir, did we already go over why we could see the moon during the daytime?
Sort of, because when I cover the moon model that we use, that lets you know what causes it to rise and set at certain times. And that specifically is the relative position of the moon, the earth, and the sun at a given phase. So in that sense, yes. So like, for instance, on that diagram, we had the earth in the middle, and then we had the 8 moons around it, and the sun was over here. If you're looking at this bottom moon right below the sun, that's third quarter. And the only way you see that is you start at midnight on the earth, at 6 a.m. on the earth, and you clearly can't see it. But by the time you get to midnight, it just rises. And then when you get to 6 a.m., it's at crossing your meridian. And then you get to noon and it disappears.
Okay.
So that's it. And basically you can look at it as it sort of rises like 49 minutes later each day. Not unlike Mars and its day, if y'all have been paying attention to the Mars rover landing. Jamon, you got a question, buddy?
I did, and it was about the moon project.
Okay.
So I've been sort of kind of lucky with my project because I have two moon phases. But my question is, since I had wrote down waxing gibbous for one day and yesterday it was another waxing gibbous, am I supposed to continue to look at it or just wait until the next moon?
No, you can get multiple waxing gibbuses. That's no problem. I like a long string of consecutive, maybe day and a half, 2 days apart observations. That's the best thing for you because you can actually see it in real time changing each day. I even would prefer to have you do several each day. I mean, every day. In other words, not several in a day, but each day do one. But again, that's all about the weather and your work schedule and all that stuff. So the more you get on a given week, that's even better because I think that allows you to really appreciate how the waxing gibbous gets a little bit brighter and brighter and brighter as time goes on. That's really the effect I'm wanting you to see. Not only that, and the fact that it's rising later and later and later every day.
Okay. And my next question is, do I have to go to the same spot when I go look at the moon? Because on a Sunday, when I did look at the moon, I was taking out the trash in my backyard. And yesterday I had went to my front yard to look at the moon. Am I supposed to stay in the same spot? Okay.
No, and in fact, if you, I mean, it's like his question about Pennsylvania. Even that's acceptable if you're getting an observation from a friend. Maybe they send you a photograph, and maybe they're halfway across the country. That's an interesting data point. Period. As long as you use their time to mark it and mark what city it was in, that should be plenty fine as well. Because you'll get the same effect. It's sort of the neat thing about the moon is we all get to experience the same phase, not necessarily at the same time because when it's daylight here 180 degrees around the other side of the earth, it's nighttime. So if we're seeing the moon during daytime, then they're not seeing it because they're at nighttime. But when their daytime comes around, they'll see the same phase we did. So
okay.
All right.
Thank you.
Good questions, everybody. Anybody else before we get cackalacken? I don't even know what that
I think Mother Nature knows that we're trying to look at the moon every night, and that's why she's giving us bad weather.
Yeah, she does that crap too. When I plan star shows, like I'll let my students come out to the observatory and where we have those big telescopes and look at it. Let everybody look at the telescopes, and every time I book one, it turns out to be a rainy night. So I think the gods just like me, or Mother Nature, or Esther, or whoever's in control of this thing. All right, folks. Well, I'm feeling pretty frisky. I got my tooth in. I'm ready to roll with the class. Are y'all ready to learn Chapter 6 material? Don't everybody jump up and speak at once. That would be sad. Make me feel good. All right. Look, this is as funny as I get. I'm an old man. I'm a dad. I got puns, and that's it. Here we go. So I'm going to share my screen that chose not to open for some reason. Okay. That's okay. I will do this again. I told this to open earlier, but it seems not to have. Maybe it will this time. Now, when it opens, it's going to be curious as to whether the green box will get around you, and it looks like it will not. Are y'all seeing the PowerPoint logo now? That's a good sign. I'm feeling better about it. So this is Chapter 6, and this is sort of the last of the material that's in the science realm. The rest of it's applying the science.
I don't know about anybody else, but I can't see it, sir.
Okay, the point's not up now. Can you see it now?
No, I just see all the files listed.
Okay, that's cool. Then I'm going to stop sharing, and I should be able to share again, and this time I'll have that window available to me. Yes. Now we're good to go. Okay, and I got to move my Zoom box because it's constantly in my freaking way. In my freaking way, man. And I'm going to do this, and I'm going to do this. And this is Chapter 6, Tools of the Astronomer. So we're going to learn about the various devices and stuff that have been invented since the advent of the telescope, including the telescope, of course. But we're going to learn a little bit about them, what the advantages and disadvantages are, all that good stuff. You can read the learning objectives in your textbook, and I highly recommend that. By the way, I tell my students on the chapters where I don't have reflection questions, and that's going to be like virtually all the future questions. Where I don't have the reflection questions, you're welcome to turn the individual learning objectives into questions and then answer them robustly and turn that in as reflection questions for that chapter. And you can even do it in addition to the regular reflection questions for more astro points if you want. So feel free to do that.
I have an astro point question.
Yes.
So say you didn't do like a chapter's astro points, are you able to go back and do them after the fact, or?
Yeah, it just doesn't help you educationally. I mean,
Okay,
it might help you for the final, but it's not going to help you for the test, which is the purpose of it. But if you're doing well enough on your test, that's not too terrible.
All right, thank
you. No problem.
Can you repeat what you said about the astro points before that one dude asked you that question?
Yeah, what I was saying was the objectives at the beginning of every chapter in your textbook, you can turn them into questions and answer those for either an additional set of reflection questions for that chapter or as a reflection question for chapters that don't have reflection questions.
Okay.
And you just turn them in, I have that link where it says chapter 1 reflection questions, chapter 2 reflection questions. Just turn it in there.
Okay.
All right.
Yeah, thank you.
No problem. So lots of opportunities to get extra points, and it also helps you learn while you go. So one of the questions they pose here, why are telescopes on mountaintops? And that's one of the things we're going to learn. Turns out, for starters, the air is really thin up there, and that makes for better seeing. That's a technical term. And it turns out that we're not closer to the stars. Okay, that's a key misconception because people think, oh yeah, we're even closer to the stars. The distance between the center of the Earth and sea level and the center of the Earth and the mountain is pretty insignificant. For instance, if you scaled the Earth up to the size or down to the size of a basketball, a individual pimple on the basketball would be larger in comparison to the diameter of the basketball than Mount Everest all the way down to the Marianas Trench would be on the Earth compared to its diameter. So literally, it's more spherical than that, than a basketball. So yeah, that's not it. But it is mostly about one, the elevation allows us to access some wavelengths that are not as easy to get at the surface of the Earth. You'll see parts of the infrared and ultraviolet don't make it all the way to the surface. So some of those you can get in the upper atmosphere from high elevations. Other ones you actually can get by flying. So we have aircraft that fly infrared telescopes, for instance, one called Sophia. So the telescopes is one of the astronomers' most important tools. And in fact, I think it was Oliver Wendell Holmes that said the starlight is the most precious thing. Everybody should get together in every community and chip in to create a telescope observatory for the whole neighborhood. And I like that idea, especially being that it's everybody chipping in of their own accord instead of the government doing it or whatever. But it tells you something about the value of starlight, and the value of starlight is that we're now analyzing starlight so much that it really is super, super valuable, even though it's so dim. You can't read by any particular star's light, but we can suck the marrow out of the bone of light and get all sorts of information that we never thought we could get before. The main purpose of a telescope is gathering light, and the main two types, at least with the visible, are reflecting and refracting. Hans Lippershey or Hans Lippershey, not sure about how to pronounce that, invented the telescope. Galileo did not do that. Okay, Galileo read about Hans Lippershey's telescope and created his own and made it better. But what he did that sort of gave him fame was we initially thought he's probably the first person to use the telescope to look at the stars. We've since found out that a guy by the name of Thomas Harriot, who was the scientist, doctor, so on and so forth on the Roanoke Island mission, i.e. the ship that came over to Manio to look for, the lost colony. It was actually the group that came after the lost colony was lost. But in that group, he actually was away in the Americas and used his telescope to look at the moon, and the dates that he wrote on there preceded the dates of Galileo. So that's kind of an interesting local tale. Of course, your your book doesn't necessarily know that. So if they ask any questions about who was the first, you're not going to see Thomas Harriot's name. So it's okay to say Galileo. I got that information, by the way, by a guy with the name Owen Gingrich, and you probably remember, or you probably don't remember it, but you did see him on the Beyond the Big Bang movie. He's now an astronomical historian, so he does the history of astronomy and stuff like that. So our eyeball is somewhat of a telescope. It's basically a small refracting telescope. So refracting just means that light has to bend because it goes from one material to another, like from air into glass, or from vacuum into air into glass, or something along those lines. So refraction actually happens whenever you go from one medium to the next. And in this case, you can see light coming in. The first thing it hits is the cornea, which is this sort of protective layer over top of the lens, the iris, and the pupil. The pupil is the hole through which we see. The iris is the sort of diaphragm that dials open and close to make it bigger and smaller. For instance, in highlight situations, it constricts the eyeball and keeps the pupil really small. But in low light situations, it opens it to allow more light in, and that's an evolutionarily useful thing. It then hits this lens, and the lens really is where the quote unquote magic happens. That's where the magnification and all that good stuff happens, and we'll talk a little bit about that later. But you can see a ray from, say, the top of a tree would hit down here in the lower part of the eyeball, and the ray from the base of a tree would actually hit around here at the upper edge of the back of the eyeball. So it actually inverts the images, and our brain just processes it like no big deal. We're used to seeing that. However, the eye is not that good in some ways. It's got a pretty good quantum efficiency. In other words, it does pretty well out of 100,000 photons that hit the rods and cones in your eye. A good fraction of them are actually signaled to the brain. So that's good quantum efficiency. I think we're only within the last 5 to 10 years did we exceed the quantum efficiency of the eyeball. So that's pretty good. Where we're lacking is we don't have much resolution, specifically because the eye hole is so small. The angular resolution depends on how big the aperture is that you're seeing through. The other problem is it's sort of like, from an evolutionary standpoint, we're a little bummed out because how we had to evolve to have eyeballs would have been something along the lines of we're possibly a sea creature, or possibly a creature that was on the surface of the earth, but either way, I mean on the dry surface, but either way, it would have been like a hollow spot, like in skin or something, that had the ability, because of its thinness and hollowness, had the ability to sense light and dark. So that would give you a relative advantage over your people that didn't have that mutation, over your critters that didn't have that mutation, because if all of a sudden you're sitting in light and then it goes black, that's a pretty good indicator that something just changed and you might want to skedaddle, right? So if you do that, then maybe you, and the percentage of the critters that have that mutation, maybe they create more offspring. Maybe they live longer too and can create even more offspring. And then in a very small number of generations, you have that new mutation as the major allele within the chromosomal pack. So that slowly evolved to other better things. But when it was all said and done, we still had those receptors pointing in such a way that they were pointing at the little surface that was near the surface of the interface between the human, the pre-human, and the air. So all these cones and rods in the back of the eyeball actually point the wrong direction. They're all pointing towards your brain. So it's sort of like building the electronics for a TV in front of the TV screen, and you have to look through the wires to see it, because all the cones and rods are pointing back, and the light's coming from this way, going, yeah, actually, I should say, all the cones and rods are pointing this way. These are the parts that read it, and light's coming from here, like this. Yeah. So it's kind of not that well designed, I would say, if you're going to use the word design on it. But evolutionarily, the way things work is you work with what you got, and you improve it as much as you can. But you can never just start over from scratch and say, well, we've learned a lot, let's start over. You can't do that in evolution. The only way you can is if one part becomes obsolete because another part does something for it, then that obsolete part might become functional in some other way and start evolving to another thing. So anyways, that's kind of a neat little tale about the eyeball. You can read stuff like that in The Greatest Show on Earth by Richard Dawkins. That's his one book that I think is not offensive, is not intentionally offensive to Christians and religious believers. So I definitely recommend that one. It's a good book. So how does light actually refract? Well, the best way to think of it is this is a light ray, the green is, and these red lines, we're going to pretend like they're marching soldiers. So these are all the marching soldiers side by side, right? And they're all marching like they're supposed to in one solid line, keeping a perfect cadence. And then they're across a sidewalk right here, and there's another sidewalk here. But in between is a big sand volleyball court, say. As they walk further and further and further, these guys on the end start to walk through the sand, and instinctively it just slows them down. There's almost nothing they can do about it. So they slow down, and then slowly the whole group of soldiers are all slowed down. And now, because they slowed down starting at that end, they've curved this way closer to this normal line. So the normal line is a line that's perpendicular to a surface. Notice it's pretty good distance away from the ray, but in here, it's actually considerably closer to the normal line the ray is. So they're walking. Then as they get here, this side again is the first to emerge, but this time they're going into a faster area out of the sand onto the sidewalk. So they start to speed up again, speed up. And because of that, now the line is farther away from the normal again. Okay. So that's literally what happens is the light in the light waves, when they enter a material other than air, they go slower. Except if they go from air to, say, a vacuum. Vacuum's faster. But the difference between vacuum speed of light and the air speed of light is very, very small. But the difference between air speed of light and glass speed of light is significant. It's like 1.5 times slower. So you can see, in some sense, there's a number called n that is actually the speed of light divided by the velocity of the light in the stuff. And the glass n is about 1.5. So that's what I mean. Sorry. So there's a schematic of what it looks like. This is it actually happening. So if you actually shoot a laser at the surface of some material other than air, obviously you can see part of it's going to reflect. That's what this part is right here. Notice that angle is the same as this angle. That's the fundamental rule of reflection. But notice also that this normal line has a pretty appreciable angle, but over here, this normal line doesn't have that big of an angle. So it did, in fact, curve closer towards the normal line, and then it curved back to parallel to its original path. It's been shifted off course now, right? It was going to go this way, but now it's still parallel to the original path. It's just been shifted over by a little bit. Okay. So that's what refraction is. And you can recognize it from your, grade 3 science course where you had a little glass of water and someone stuck a pencil in it and the pencil looked broke or bent. That was refraction. That was the model of refraction that probably everybody remembers. This is how the rays of light come together in a refracting telescope. So a refracting telescope will have a lens, and the lens can be double convex like this is. Convex means bubbling out, and concave means sort of bubbling in, right? Turns out we actually have lenses that are convex, maybe convex at a different radius of curvature, and then another convex, but again, a different radius of curvature. We even have concave, convex, and concave. But this is what we call a converging lens because it's double convex. And what happens is each location where this light hits, it turns closer to the normal. So that sets up its new direction. And then when it leaves, it goes back farther from the normal, which you can see is like this angle now. And it turns out that almost all the light that goes through here, almost all hits the same spot. And the distance from the center of the center line of the lens to that spot would be called the focal length. Okay. Now, if they actually made this lens in the shape of a parabola as opposed to part of a sphere, it would be much better in that all the points of light would come to the exact same spot. But because they made it out of a sphere, which is much cheaper to make, you're going to have something called chromatic aberration. where basically different, well, excuse me, spherical aberration. That's going to cause it to basically have different focal points just a little bit off. Okay, chromatic aberration is about the color. We'll learn about that in a second. So, anyways, this is the objective lens, and that would be like at the front of your telescope. And what it does, it brings light down to a single focus in principle. So this would be the focal length for the front lens, and those are normally mounted in a telescope in such a way that you can't just take them out. And there's good reason for that. If you actually try to take them out and put a different focal length lens in there, it's a big process to make sure they're aligned properly and all that good stuff. Is a pain in the butt. So they normally just mount the objective lens or the primary lens in a permanent way, so you can't take it out. Now it'll have a focal point somewhere back here, and the distance between the center of the lens and the focal point will be the focal length. So then you put an eyepiece over here where its focal point, which is again another lens like this, but its focal point will be right in line in the exact same spot with this focal point. That's how you focus. You turn that little knob on a telescope or a microscope, you're getting the focal points to match, to hit the same spot. When they do, then it's in focus, and you're actually using this to magnify the image, if you will. Okay. You can see that that might cause a problem, because it turns out most things are better when the focal length is longer. So the longer focal length, which is really like half the radius, if you're using a spherical mirror, it's half the radius of the sphere that this would be part of. So if you make the sphere bigger and bigger and bigger, you make the focal length bigger, bigger and bigger. Turns out when you make the focal length bigger, bigger and bigger, the spherical aberration isn't as bad. The chromatic aberration isn't as bad. All sorts of good stuff. So it's really, really super helpful. But anyways, we'll talk about that again in a second. It also magnifies better. So here's the reason that the focal length magnifies better when it's a longer focal length. So you can imagine a ray from the top edge of sight and then a different ray from the bottom edge of sight. In other words, you're looking to the fullest extent of the telescope width-wise. This one coming from above, say the red one, that red one will end up way down here on this side. This blue one will end up way up here on this side. Notice it's inverted, just like we did with the other eyeball, with the eyeball lens. And you see that the image wouldn't be that big. It's just from this blue point to this red point. However, if you take a telescope that has a longer focal length, notice how much flatter that looks than these up here. Now this one from a wider, from the top, comes way down here, and this one from the bottom comes way up here. Notice how much bigger that image is. So that's why the larger focal length makes for a bigger image and therefore more magnification. In fact, I'm going to give you a formula for magnification later, and it's mainly for you to understand how to use a telescope. So I'll show you that a little bit later. The aperture sets the light collecting power. So one of the ways I've heard telescopes defined is that it's a bucket meant to catch light, not unlike a bucket meant to catch rain, right? If you're on Survivor and you need rain to get water, right, the bigger around the bucket that you have, the more rain you're going to catch. Same thing with a telescope. The bigger diameter of the telescope, the more light you can catch. So if you're looking at telescopes of all equal quality in terms of lenses and purity and quality of handling weather and not breaking and stuff like that, if you're looking at all equal quality, what you want to do is find the largest telescope that you can afford, and that will not be so large that it prevents you from using it. I went out and bought a 12-inch telescope for the other college I was at before this one, and I was really excited because I had a buttload of money and had to spend it because we were getting all new equipment. And I bought a $20,000 telescope that was 12 inches, and the sucker weighed 167 pounds. So that became a awesome telescope that was rarely used because I literally had to carry it up and down steps and then put it together by lifting it up and putting it on a tripod, and it was just hard. And they hired a quite a bit smaller person than me later, and that person had no hopes of lifting the thing. So you got to watch out for that. Be practical. Don't just go out and get a 12-inch because you can get a 12-inch. Maybe consider an 8-inch, which is really nice, or a 10-inch, which is really nice, but a lot easier to run around with. So remember, the diameter is really the most important thing about a telescope, because that one allows for more light gathering power, and two allows for better resolution. Okay. And you also want the longer focal length that you can, because that provides for better magnification, which is actually probably the least important parameter that astronomers care about. They don't care that much about magnification. So when you go into Walmart or CVS and you see some telescope for sale, they almost always magnifies 400 times or something like that. That's their big selling point. But the magnification really is not that important unless you're just using it, as a voyeur or peeping Tom or something. It might help you a little bit looking at your neighbors and find out whether they're stealing your mail or something. All right, so here is the last kick butt refracting telescope that was really built. Anyways, this is at the Yorkshire Observatory. If I remember correctly, this is like in, I want to say either Missouri or Wisconsin or something like that, but it's run by University of Chicago, and it's a 1 meter lens up here in the front, and it has a long focal length, as you can tell. In fact, this is, if I remember correctly, this is like 60 feet long. So it's really, you can tell, here's a dude, and that dude is, like maybe 1/10 the length of that. But it was a kick butt telescope, and really the problem is refracting telescopes got a lot of stuff wrong and got a lot of reasons to not be used unless that's all you can afford. Okay. Mainly, and I'm going to discuss those problems in a second, but look at this one. This one's so long.
Excuse me?
He can't even see up. He can't even look up towards the top of the sky, because how could it tilt? Yes, go ahead.
If the refracting telescopes have so many problems with them, then why'd they make one so big?
They still have, a 1 meter telescope is super valuable, and you can do a lot of discovery with a refracting telescope. Anyway, it's really better. Refracting telescopes, people use them usually for looking at planets where you got plenty of light. So that's why. But to be honest with you, you pretty much don't have too many large refracting telescopes that are used at the research level anymore. We have a research level refracting telescope that costs, check this out, we got a 20-inch reflector that cost us like 60 grand. Then we got a 6-inch Takahashi that is infinitely more high quality than the nice 20-inch we had, and it costs like $35,000, and it's only 6-inch. So there is a good place for refracting telescopes, but it's mostly for looking locally, like in planets and stuff like that. At least that's been my experience. Okay. So yeah, they shut this down. It's kind of a bummer. I was hoping maybe someone would buy it and make it a public thing where people could come in and, open to the public. They could have someone that staffs the place and runs it, but kids and grown-ups could come and look through telescopes. I mean, imagine being able to look through a 1 meter telescope. That's freaking awesome. The largest telescope I ever got to look through was a 24-inch. And that was at Chapel Hill, what was like the worst place in the world to have it, because it was right on Franklin Street. So it's all this, light pollution and stuff, but it was still a beautiful telescope. I think it cost $150,000 back in 1970. So it's a pretty beastly piece of equipment. So here's some of the problems with refracting telescopes. You see this big chunk of glass? Well, of course, you always want your aperture to be big as possible. So that means you're going to have a bigger and bigger piece of glass. And the whole piece of glass has to be perfectly pristine. It can't have air bubbles and gnats and crap like that in it, right? And then you've got to not only grind one side to perfection, you got to grind two sides to perfection. And then, since the light has to go through it, you actually only can grab it near the edges. In other words, if you have to affix it to like the telescope, it's only the edges of the glass lens that you can hold it by, because if you didn't, if you held it by some other part, you're taking away some of the light, which is the whole purpose of making it big to begin with. So that's a problem. The other big problem, in addition to spherical aberration, which we already talked about, is the chromatic aberration. And that chromos means color, and it literally means that basically blue will focus at one point, green will do another point, red will do another point, yellow another point, so on and so forth. So what happens when you look through a telescope with chromatic aberration, even if you focus it, it's still going to see this. You'll have a white dot for a star, and it'll have a little ring of rainbow around it, and that's chromatic aberration. You can use catadioptrics, which is various types of lenses you can put in front of it to get rid of things like chromatic aberration and spherical aberration and that kind of stuff. But that's really a problem. But the bigger problem that I'd like to talk about is how much light is stolen by absorption in the glass. So I have a wonderful example to give you about this. I'm going to stop sharing for a second, and I'm going to turn on my document cam. And I want you to think about driving. Okay, so you're driving down the road. Your rearview mirror is this object. Okay, it's basically a plate of glass that's probably a 1/16 to 3/16 of an inch thick, and it's got a little holder. It's got a little holder. And then it's got a little ball back here so it can pivot and axis, and it's got a little lever up here. Okay, and unlike a lot of levers, like light switches and that are single pole light switches, if you turn it one way, the light goes off. You turn it the other way, the light goes on, and that's it. Period. This one works no matter where it's at. You just put it to the other, and it does what you need it to do. So what happens is you get light coming from some jerk behind you, running with his high beams on, and then the law of reflection says that the angle of incidence has got to equal the angle of reflection. So it comes back right here and hits you right in the eye. That's a pain, right? So you don't like that. You don't want the bright lights in your eyes. So you immediately decide to flip that little lever. Okay. Well, you flip that little lever, say this way, and now it's like that. Then all of a sudden your mirror is in a slightly different position. In fact, your mirror now might be, say, like this. Okay, so that same light's now hitting it, but now because the normal line is over here, it has to come back at this spot, and that now, because you chose to push it forward, that is now hitting you in your chest. And sometimes you can see if it's that way, it's either going to hit you in your chest, or if you do it the other way, it's going to hit over top of your head. But it hits in your chest. But look what happens to the ray as well. The ray also, like it did before, but I didn't choose to draw it, will also refract. So it tries to get further from the normal, which would be like this, and then it bounces off the back, which is reflection, and then it curves back sort of the same direction it was going. So now it's in your eye. So literally that light you see when you go from the high beams messing up your eyes to the high beams not being a problem whatsoever, that darkness is entirely due to the light being absorbed, the energy of the light being absorbed by entering the glass, by traveling through the glass. Have y'all seen that effect? How big of an effect that is on the brightness? Anybody seen it before? Hey, y'all drive, right?
Yes.
Yeah, I've seen it. I've seen it before.
So that's why that is, and you can actually see this on all mirrors. Very few mirrors are front silvered. So you can look, for instance, especially if you have any kind of orthodonture or dental work in your mouth, like fillings and braces and stuff like that. If you look really close to your bathroom mirror, you will see not only your image that's really bright, you'll see a slightly dimmer image behind it, and you actually might see 5 or 6 depending on how closely you look, because of course that first one's going to bounce off, but then it could bounce off the front surface and reflect again, and you'll get a second image and bounce off the front surface and reflect again and get a third image, and so on and so forth, each one being consecutively dimmer than the last. So that's a neat little effect that happens because of the absorption of glass by refraction. So if the whole purpose is to capture photons, the whole purpose of the telescope is to capture as many photons as possible, then using a refractor really makes that a problem because it's sucking up a bunch of photons. So that's another reason. I'm gonna go back to sharing my screen now. So your book lists them, but I wanted to make sure you heard all these different reasons that I've been mentioning, not just the ones that are in your book. Oops, I got to touch the screen first before it lets me use the buttons. Okay, so eventually we go to reflection and reflecting telescopes, and I believe it's thought mostly, I think the history is pretty certain that the reflecting telescope was invented by Isaac Newton. And turns out you can do the same cool things. You can actually magnify images and collect more images just by using reflective surfaces. And when you use that, mirrors instead of actual lenses, then you degrade the light less. Okay. As I said, the rule for reflection is the angle of incidence equals the angle of reflection. So if this is 45 degrees, this will be 45 degrees. And normally we would do like an optics lab if we were teaching this class and without quarantine. We do one little optics lab where you had some lenses and you show and some black blocks of glass too, so you can see that refraction happens and all that good stuff. But all you can do here is, if you want to, you can play with a program. Actually, I might do that. Maybe I'll make that a lab. I won't tell you so much about that yet. Okay. All right. So here's the idea of a reflecting telescope, and this is either Newton's telescope or the a replica of Newton's telescope. I think Cambridge has his actual telescope, but I think he made several replicas, and we've got one of them here in the United States. Probably a couple ones like it that are mock up, but I think we have one that was originally made by him as well. So basically, it's really small too. This is only like maybe 12 inches long. Okay, so it's a really, really small telescope. But one of the advantages of a reflecting telescope is, remember how long that telescope had to be with the refractor? Well, this one allows you to bend the cone of light on itself. So starlight comes in a Newtonian telescope like it is here. This is a Newtonian, and bounces off the primary mirror, which, by the way, the primary or objective mirror on a reflecting telescope is at the back, whereas in a refracting, it's at the front. So it bounces off that and comes back trying to get to its focal point, which would probably be roughly here. But Newton had the great idea of putting a small mirror at a 45-degree angle and sending the light out the side. So now the focal point for that first lens is here. And if this one's curved, they could actually adjust that a little bit too by making a curved lens here, or a curved mirror here. But that's, just details. Either way, you get a focal point. And then you take and put an eyepiece in there and you adjust it by focusing it until the eyepiece focal point is at the same place as the focal point from here. And then this eyepiece is actually magnifying the image. So when you see a telescope that looks like someone's looking at it weirdly, like they're close to the business end looking at it, it's a Newtonian telescope. Another good idea was, instead of taking this mirror and putting it at 45, you could actually put it perpendicular to the rays that are coming in and shoot the reflection straight back here, and then drill a small hole in the back of the telescope. Then you're looking through it just like you would a regular refracting telescope or binoculars or anything else. That's called a cassegrain. Cassegrain. This is a Newtonian. Shoot it through the end. It's a cassegrain. You can also shoot this through the side, but not send it to an eyepiece, but send it right through the axle that allows the telescope to rotate back and forth. And if you send it through that axle, you could basically pipe it into another room where the image can be analyzed, and that's called a coude focus, C-O-U-D-E, I think with a little squiggly over the E or something like that. That's a coude focus. Or you can have a direct focus where literally you have a little man sitting up here in the front and they look at a little eye hole where this focal point comes in. Telescopes nowadays are so big that a human being in front of it's not that big a deal. You're not losing too much light. So that's another way you could do it, direct focus. But that's often, modern telescopes are so big, you don't look through them with eyepieces. You could mount, for instance, a CCD or some other type of electronic camera or something right here, and then just let the light fall right on it, and then look at the image that's sent to you via electronics. Okay. So see the words primary and secondary and that sort of thing. So those are the practicalities of telescopes. And the largest telescopes in the world are reflectors. Reflectors have several advantages. There's no chromatic aberration because the light's never actually piercing a surface going into another material. They can still have this the spherical aberration, stigmatism type stuff. And mirrors are, of course, you only have to polish one side. You can hold the edges plus the entire back. For instance, you could glue them onto something and the individual mirrors onto something. Or in this case, they actually made them out of individual tiles, sexagon, whatever that shape is, six-sided shape. You can make them in a tile shape like that and just put them together. And you could, in principle, put them on little motors, basically, that would allow them to twist and turn and stuff like that. And that's called active optics, which your book doesn't mention, but you can do that to counteract some effects of the atmosphere and heating and stuff like that. Or you can do it even some other cool things, not with those, but just by analyzing the starlight and then sort of doing what your noise canceling headphones do. Your noise canceling headphones hear a sound that's not coming from the speaker that you're wishing to listen to. So they work out the mathematics of what that sound is and quickly do the opposite of it and put that on top of your music, so it cancels out the actual gaudy sound, if you will. So we can do that same thing with light, and that's called adaptive optics. So let me show you some things about telescopes in general. I'm going to stop sharing my screen for a second. Go back to here. So from least important to most important, the powers of a telescope are magnification power. See, so I'll call them all of them powers, and that gives me a little bit of freedom where I don't have to think about the actual formulas so much. This one, I am going to think of the formula. I'm not requiring you to do any math with it, but the magnification of an object, as seen from a telescope, is the focal length of the objective divided by the focal length of the eyepiece. Okay. Now, remember, I told you the focal length of the objectives is sort of set. That's, when you buy a telescope, you get that focal length, and that's all the focal length you're ever going to have. But notice, are M and focal length of the objective, are they thumbs up, or thumbs up, thumbs down? Can y'all tell me what two things have to be true for it to be thumbs up, thumbs up? Opposite side of the equal sign, and then what?
Over the...
Yeah, the same side of the fraction bar, right?
Yeah.
Yesterday a student told me very directly that she didn't understand this basic process. So let me back up and show you this thumbs up, thumbs down thing. Let's take the equation y equals, so just break off from this a second and just follow me. Let's take equation y equals k times x. And let's pretend k is, say, 2. Okay? Let's take and consider the case of x equals 1. Then y would equal 2 times 1 equals 2, right? Now, let's double. Yes, you could say that, Jemine. Now, let's double x. So instead of x being 1, let's let x be 2. So now I'm going to say y is equal to, remember, k stays the same, so that's 2. But now x is 2, and you get 2 times 2 is 4. So you see that when x doubled, I multiplied x by 2 and got a y that was bigger by 2, because x was 1. If I multiply 1 by 2, I get 2. And sure enough, y was 2, and I multiply 2 by 2, and I get 4. So that's thumbs up, thumbs up. That's what I mean. The x went up, the y went up by the same factor. Now, putting exponents and stuff like that up there, that's a whole different ballgame, but this is the first rudiments. This is just trying to say whether they're directly related, meaning one goes up, the other goes up, or whether they're indirectly related, which would be represented by this. So let's say y equals k over x, and let's let k equal 4 for this one. Okay? So let's consider the case of x equals 1. Then you get y equals 4 over 1, which equals, anybody? 4 divided by 1 is?
4.
4. Now let's try doubling x. Let's say y equals, remember, k stays the same. So now I'm going to use x equals 2. So 4 divided by 2 is?
2.
So in this case, I multiplied the first x by 2 and got 2. So my x went up, but my y actually went down by a factor of 2. That's what I mean by thumbs up, thumbs down. Now do you see why I say if they're on the same side of the fraction bar, but opposite sides of the equal, then they're thumbs up, thumbs up. But if they're on the opposite sides of the fraction bar and the opposite sides of the equals, this one's down below, this one's up top, then they're thumbs up, thumbs down. Does that make some sense? Well, hopefully that helps you anyways. So when I look at this, yes.
Is there anywhere we could go to understand this better and look at it more thoroughly? Is there any place in the book?
maybe the opening chapter where it talked a little bit about science and graphing. But you could, what I always do is I just have students put this stuff like in Excel spreadsheet, put one of these equations in there and then throw numbers in and see how it works. For instance, you could do the same thing, put in one column x equals 1, x equals 2, x equals 3, x equals 4, and then say y equals kx, and that'll give you what y is. And then you can say y equals kx squared, and that will give you what y is when x is squared and x cubed. And then you can do the same thing with 1 over x, 1 over, or k over x squared, k over x to the fourth. That's about it, but I'll think about it. I know I have a lab that handles a little bit of this, but it's a little too much algebra intensive. So, but let me think about that a little bit. Okay.
Okay. Thank you.
You can look on Khan Academy for proportional. Also, there's the word directly related in math now, and inversely proportional are indirectly related. That's the sort of math that we're doing when we say something's directly related. We assume there's a constant between them, and then you usually give them some x and y data so you can figure out what the constant is, and then they give you another x and ask you what the y will be now, something like that. So if you look on Khan Academy and you look for these relationships, like in Algebra 1, that'll show you the mathematics of why this is. Okay. Now, on this case, is m in the numerator or the denominator? Denominator starts with a D and means down on the bottom. So is the m in the numerator or the denominator?
Numerator.
Numerator. What about F0? The objective one, FO.
Numerator.
So they're thumbs up, or thumbs up, thumbs down?
Thumbs up, thumbs up.
Thumbs up.
Exactly. So M and F0 or FO are thumbs up, thumbs up. They're 2-2. Okay. So that means if I double the focal length of my primary mirror, I'm going to double my magnification. So yes, a 1.6 meter focal length telescope is better than a 1.0 meter focal length telescope. Okay. But the more important thing, and this is the relationship between the magnification and the eyepiece. So let's say you've got this really good image of Jupiter that you're looking at, and Jupiter and Saturn are two of the coolest planets to look at, by the way, and they really steal the show compared to stars in most cases. But if you're looking at what looks like a good image of Jupiter, but it's really small and you can't see details very much, in the night it's really clear, so you feel like the haze isn't going to bother you. Let's say you see that image and you really like it, and you're using a 18 millimeter eyepiece. What I want you to tell me is if you also have a 12 millimeter and you also have a 20 millimeter eyepiece, which one do you switch to better magnify the image of Jupiter? You're on the 18. Which one would you want to use, the 12 or the 20?
Is it 12?
Yes, because this and this are thumbs up, thumbs down. So I want my magnification to go up. That means I need my F of my eyepiece to go down. So I go from the 18 to the 12. Good job, Tyler. So that's the real practical implications of thumbs up, thumbs down in an everyday sort of life scenario. When you're looking through a telescope and you just want to make the image bigger, yeah, you make a smaller eyepiece. Okay. So magnification is the least important of the powers of a telescope. That's why I put it up here under least important, but it's not the only one. Turns out in most applications, people care more about the light gathering power and less about resolution. But in other research and other times, you might need the resolution. So these last two powers will change places in the hierarchy of least important to most important. So one of them is the resolving power. And I say it this way because I don't want you thinking about the resolution, because that's a weird parameter. Resolution is basically an angle, And the smaller the angle, the better the resolution. So it's got this weird thing where you want something to be really, really small, where people normally think of good as big, right? So the resolving power goes up when your resolution gets better. That corresponds, of course, to that small angle. And what resolution is really is how close together can two things be measured by angles as opposed by inches. How close together can two things be where you still see them as two separate items? You know, if you're driving on a really long straight interstate at night, when you first see a car way up in the distance from you, you probably can't tell that there's two headlights. So there's a brief time where you don't know if it's a motorcycle or a car with one headlight, right? That's because it's resolving power of your eye is insufficient to see whether or not it has two lights. But eventually they'll get close enough where the angle of separation between the two lights, if it is a car with two headlights, will actually be seen as two separate lights. That's what we're talking about, resolution. And it turns out the resolution power is directly related to the diameter of the telescope and inversely related to the wavelength, okay? What I mean by that is if I want my resolving power to improve, I want the diameter of the telescope to go up. So RP and diameter are thumbs up, thumbs up. Okay. But notice resolution power and wavelength, and I mean the wavelength of the light you're looking at, is thumbs up, thumbs down. Okay. So this is why if you've ever seen Green Bank Radio Observatory or Arecibo radio telescope or the new one in China, these suckers are big because they're radio telescopes. And remember, our great mnemonic, great excess undermines various industries' Marxism rules. And remember, that's me paying homage to the late Rush Limbaugh and making a joke. I'm not really supporting Marxism, but you know, there's some truth in that statement. But again, I don't support Marxism. So with that, you realize, wait a second, the radio end is the long wavelength end. So if I want to get any decent resolution, meaning I want to see parts of a thing as separate parts, then if I'm using a really big wavelength, I'm going to have to compensate for that big wavelength by using a really huge diameter. Okay. So that's for resolution power. And the last one is light gathering power. And it's really equal to pi times the diameter squared over 4, essentially. And this is most important. Okay, so in this case, light gathering power is directly related to diameter as well. In other words, it's thumbs up, but it's thumbs up squared. So LGP and diameter are thumbs up squared. What do I mean by that? Well, if you took a photograph with a CCD or regular film or whatever of the Andromeda Galaxy, and you were using a 10-inch telescope, and it came out perfect when you exposed it to 30 minutes of looking at Andromeda. In other words, you open the aperture of the camera for a whole 30 minutes, and slowly but surely photons just build up, and then you put that image together, and it was like the perfect picture. You want to get another one just like it. Well, if you use, instead of a 10-inch telescope, you use a 100-inch telescope, so the D went up by a factor of 10, then the light gathering power would actually go up by a factor of 10 squared, or 100. So you could now, instead of taking 30 minutes, which by the way, 30 minutes is what, 1,800 seconds. So you could take it just 18 seconds with a 100-inch telescope compared to a 10-inch telescope. So that's one of the ways you can think of light gathering power. So 10-inch required 30 minutes, which is 1,800 seconds, but a 100-inch only took 18 seconds.
Okay,
that's the beauty of light gathering. Yes.
Is the time correlating to how much time it needs to gather light, or to fix itself in a direction? I can't.
Yeah, it's actually just how much time it needs to gathering light. You'd have, if you're taking such a photo, you have a tracking mechanism that tracks and continually fixes your telescope to make sure it's not losing its exact position that it's looking at as the photograph is being taken. So the 30 minutes is just how long it takes to get enough photons onto the CCD or film so that the image looks really good. For instance, I showed you that Hubble deep field picture. That was a photograph taken by Hubble, which is literally like 3 meters across. It's like 12 feet almost across the Hubble Space Telescope. And it looked at a pitch black area of the sky that was really small. I think I told you it's like looking through a wedding band on the end of a pier and you're up at the street. Looked in an area that small that looked pitch black, and they left the aperture open for 11 days straight, essentially. So some things are so faint, you just need a lot of photons before they start to show up. And in that image, we were able to estimate the number of galaxies in our observable universe. Okay, so that's what light gathering power is about. Does that help you guys understand a little bit? So notice all the powers all depend on the diameter of the telescope, except for the magnification. The magnification is sort of something that's set in, and that's why I told you it's not that important. But all the other ones depend on diameter in a good way, meaning the bigger the diameter, the better the telescope. So if you want to buy the best telescope you can, again, buy the biggest you can afford, and one that's not so big that you're not going to use because it's cumbersome. Okay. So the refracting telescopes are obviously a lot smaller because the light can bend over on itself. They're cheaper to build. You can actually make them large a lot less expensively, so on and so forth. We do, of course, put telescopes in space too, and they're of all types, reflecting telescopes, as well as infrared telescopes, all sorts of cool stuff. So here's some of the world's largest telescopes. You might just keep an eye on those for news and stuff like that. Of course, we did lose the telescope in Puerto Rico, so that one's no longer functional. It's literally falling apart from disrepair. But
what happened to it?
We just didn't maintain it. I don't think we ever put it in the money to maintain it. I don't think they had any intention of supporting it for very long. So it basically, in the salt air of Puerto Rico, it got rusted and parts just fell off one by one.
And also the hurricane destroyed parts of the building.
I think one of the towers got messed up in that last big hurricane. So yeah, it was a bad loss. But China, you'll see a picture of China's now. That's even bigger than Arecibo. So this is the resolution thing I was talking about. So initially, when you see a car that's too far off in the distance for your eye to resolve the two headlights, you might see a sort of a monolight like this. But as it gets closer to you, your eyes can separate it and see two distinct lights. The smallest angle between two objects, where the two objects appear to be two angles, is called the resolution. And that's why it's something that's really small. That's why I like using the phrase resolution power, because I never make you do the calculation or anything. Okay. But you can actually figure out a theoretical maximum of that on a telescope just by doing some calculations. What you have to do is pretend that the whole opening or the pupil of your eyeball or the aperture of the telescope, each little point in that telescope hole acts as a separate source of light. So it's just like that time where I told you to put your index fingerprint right next to your thumb fingerprint and look at a light, and you saw those little images in between it, because every point between your thumbprint and your fingerprint acted as a separate source of light, and those light interacted with each other so that troughs lined up with troughs and crests lined up with crests, giving you all the light coming through really brightly. The other cases, basically a trough lined up with a crest, and the light canceled out, and you got a repeat of the actual outline of the fingerprints. So the same thing's happening here, and each one of these little points in between here and here acts as a separate source of light and starts to cancel each other out and makes it where you just can't see the details enough. When you do that calculation, there is an actual formula for the resolution of a telescope, and you can only get that like if you're at Hubble, because it'd have to be out in outer space. Otherwise, diffraction limit is almost meaningless, because in the air, the atmosphere is going to jack it up way more. But it turns out we've done something great that allows us to do an even better job with that, and I'll show you that in a second. So astronomical seeing really is the technical term, but basically, you know, turbulence in the air can take light and bend it. Remember, light, when it goes from one material to the next, it actually curves and bends and stuff like that. Well, that's what happened when light goes through clouds. It goes through high density air pockets, low density air pockets. All that stuff's going to change it, and it's going to disturb your seeing. And no matter what magnification you use, it's still going to be jacked up. In fact, when you increase the magnification, you just get magnified crap. Okay, so what we've come up with is a system called adaptive optics, and it's so good that this is a photograph you take without adaptive optics, this one on the left, and the one on the right is when you did the same setup, only you used adaptive optics. So now on Earth, you know, at least in decent weather conditions, we can get images that approach that of Hubble, but we don't have to put it in space, which is so expensive. Okay, so these now can actually compete with Hubble just on a resolution standpoint. So back to the eye, the major factors in looking at objects in the night sky is integration time, quantum efficiency, aperture size, and focal length, right? Well, the integration time is one of the killers for the eyeball. The eyeball basically collects photons on your cones and rods for a certain amount of time, and then it sends them off to the brain. Then it does it again, sends it off to the brain, does it again, sends it. But you can't lengthen that time. So if you're looking at something really dim, you might not ever get to see it because they didn't. You didn't look at the thing long enough for one signal to be sent up. And you know, some of the photons are going to be lost by quantum inefficiency, anyways. So as I said, our eyes are pretty good quantum efficiency wise. It was only I think in the last 5 to 10 years that modern CCDs got as good a quantum efficiency as the cones and rods did. But the CCD and other types of instruments have way better integration time. Even plain film, which is what we started using, is a glass plate that you put a film on, and then the light, the photons actually hitting the film would sort of burn it into place. And then you go in and wash it off, and all that's left is all the spots that were dried by the light. So you end up getting a negative. In other words, all the stars would be black dots. And then you can make an actual, take that negative and make an actual photograph of it if you wish, or you can just look at the negative directly. And that's like Henry Swan Leavitt and other great calculators did back in the day. But now they use CCDs, and the CCD is even better. So these are the kind of things you can get, not only without the photography. The only thing you could do is communicate with other researchers by drawings that you made. So getting photography in was a big leap. Getting in CCD photography was an even bigger leap. So this is a CCD. This is what it looks like. Like each of these is a little pixel. It's sort of like a light emitting diode. Except that if you actually shine light on a light emitting diode, it actually can absorb the light. And you can set this to absorb the light, and it's going to record the energy, the brightness of the light. It can record, say, the wavelength of the light, so you know the color. It can tell you what time of day the light came, and it can tell you from what coordinate on the pixel board it came from. And then it sends it off as just ones and zeros, which is the language of the computer already. So it's already, you know, in the computer where you can process the signal to get as much out of it as possible. So CCD is a great thing. And it was developed essentially by physicists and astronomers, mostly working for the military. You know, the military has done a lot for scientists, and scientists have done a lot for the military, specifically because they find someone that's a scientist that's really good at something, and they know they have a very specific application they want. So they set us to do things like design cameras that can get really good resolution so we can spy or stuff like that. Ultimately, that stuff trickles down into the regular economy, and that's why all of a sudden iPhones have, fairly good cameras, and other phones of course do too, but phones have very good cameras, and it all started with physicists working for the military. Kind of neat, huh? The other thing is also the physicists and the military still have the best CCDs because they're on the front lines of research. You might actually be now at this point starting to compete with actual companies that are making them. So though we had a head start, the companies might actually be exceeding us now. But generally speaking, the best cameras are at research institutes and in the military, are at research in the private sector. Okay. So that's the CCDs. One of the other important things is a spectrograph. This is what allows us to get those spectra that Kirchhoff's rules told us about. So you send light from a telescope through a slit. The light then hits a mirror. The mirror reflects it to a diffraction grating. This used to be a prism, but we showed you what happens to the light when it goes through glass. It actually loses all its brightness. We found that it can do the same thing if you just put a series of little notches or imperfections on the surface. You've also seen this when you look at light bouncing off a DVD or a CD, you see that rainbow. That's basically all that is. You can actually make a spectrograph with a CD or a DVD. It will then bounce off another mirror and be sent to a CCD, and the CCD will then have all the colors laid out in a very distinct little box, like those bright line spectra I show you and the dark line spectra I show you. Here's the profile. This is the great excess undermines various industries' Marxism rules, and it shows you where the atmosphere is actually transparent. It's 100% transparent up here, and it's 0% transparent here. In other words, it's opaque. So you can see that the radio wavelengths, at least up to about 10 meters, is transparent. Our atmosphere is transparent to that. It gets a little shaky around the 10 to the -2, around the centimeter mark, but we can get even at altitudes, and so on and so forth. And then around here, it's pretty crappy in the infrared, but you get to the visible, and it's essentially transparent. Then you get, of course, to the ultraviolet, and it goes to crap again. And here's various telescopes that look at each of those things. Gamma rays, notice it's opaque. Wherever it's opaque, you're going to have to put the thing in space. Where it's somewhere in between, you're either going to have to go to altitude or you're going to have to go in space. So that's what all these telescopes are about. This is the new, This is the new version of Arecibo. This is what China built, and you can see it's really big. And China has really beautiful mountains, but that's pretty awesome.
2 minutes left.
What's that?
2 minutes left.
Thank you, sir. This is what Green Bank Radio Observatory, another big radio telescope. This is a very large array. We can connect telescopes over large distances, like from here to here, and we can pretend this telescope is that big from a resolution standpoint by using interferometry. And that's basically computer programmers writing programs that allow the signal from this telescope to be combined with the signals from all these telescopes. And we get this big array acting like one big telescope that's lens is this, that's aperture is this big, right? Now the light gathering power is no bigger than the sum of the individual light disks, but the resolution is bigger. So in principle, if we put one on Earth and one on the sun, we could literally get a telescope whose resolution power is the same as a telescope as big as 60 Earth radii. There's Sophia flying over, getting infrared. Satellites also detect ultraviolet and X-rays, and the Hubble Space Telescope can do some of that too. There's some of the space observatories. We get other information by flybys, landers, rovers. People actually went to the moon. That's not a hoax. And from that, we get really good information. The Large Hadron Collider is another place because we're studying such high energies for the Big Bang. The only place we make energies comparable and can see what's going on at that temperature and that energy is in colliders like the Large Hadron Collider. Notice that's a person down there to give you some sense of scale. Also Ligo and neutrino detectors. This one, we can detect neutrinos. In September 2015, we got Ligo online, and in a very short period of time, it detected the gravitational waves that Einstein's equations predicted from 1915. That was the first confirmation that gravity waves existed. It was also the first confirmation of direct evidence of a black hole. It was also direct evidence of two black holes colliding, and it was also direct evidence that Einstein's equations are exactly right when used to calculate the gravitational wave signatures of two black holes colliding. So it's a very big deal. But most recently, we had a young lady who, as a small child, said she wanted to take a picture of a black hole. And just last year, as a graduate student, she took the first ever photograph of a black hole. I really should commit her name to memory. She has not done anything else, of course, because she's still she's probably finished by now. But either way, that's a really big accomplishment. And I love the idea of a little girl thinking about doing that and then doing it. We also have computers, which is super helpful. So
is that Nobel Prize worthy?
I wouldn't say necessarily that's Nobel Prize worthy because we were just literally a step away from it. But it's hard enough that I would say maybe she's might be on a Nobel Prize track, but not necessarily just for that. I just don't think that's big enough. That's all encompassing enough, but it is still a big deal. So the last thing I was saying is just with computers, we can model galaxies and actually do the calculations of billions of particles and get simulations that come out and then compare them to reality. And these computer simulations predict models that look so much like real photographs. It's just amazing. And that's it. That's the entirety of chapter 6. So y'all are certainly capable of doing chapter 6 now, and the homework and all that stuff. Everybody, of course, is free to go. I will wait here for the last person to leave. Y'all have a test open right now? I can't remember.
Is it the Constellation Quiz number 1?
Yeah, that's not happening. So like I said, we're not doing constellation quizzes. The worst thing that might happen is, like I said, I might take a photograph without the words on it, or a picture from, like Gibbon Smith website without the words on it, and put that as a question and multiple choice and ask you which constellation it is. So just be prepared for something like that. So do your little labs, finding Ursa Major and using Ursa Major labs.
So don't do the thing that's right under our meeting window, right?
Don't do Constellation Quiz.
Yeah.
Okay.
Yeah, that's nothing useful there.
Okay. One more question from me.
Yeah.
The SmartWorks homework, even when I press the review thing, it's still not going into grades.
Yeah, I gave her an idea that what if I erase it and then crank it up again, create it again. She said that might work. If it doesn't, then I'm supposed to contact her. But what I'm going to be doing is I'm going to one by one, and this is a painful, slow process. One by one, I'm going to erase the homework assignments I put up, and then I'll send you an email and say, hey, could all y'all go click on your homework assignment again and see if it comes over. Don't worry, I'm getting your stuff because I can always go over and download it from the SmartWorks side. It's just right now it's not being used in the calculation for your grade on Canvas, so that's kind of a pain.
So we have to redo our homeworks?
No, you just got to click on it again, just like you already did. I will let you know when you need to do that, but and I'm not sure it's going to even work, but we'll see. I have the Norton people working on it.
Okay. Have you sent out any emails yet?
About that?
Yeah.
Just that first one where I told everybody to try it, and now I've seen that it don't work, so I have to do something else. So yeah, I'll send it to you. And it's not, like I said, this isn't something that would harm your grade for not doing. I just really want you to do it. So when I do send it, just read your emails. I try not to send out too many emails for that reason because I don't want students to ignore them. But who else has a question? Anyone? Amanda?
And I have one more question. Okay, my first test is still not graded.
Okay, I will work on that. I didn't do anything related to that this weekend, but I'll work on those.
Okay, thank you, sir.
All right, see you. Amanda, you have a question, or Amy?
Have a very nice day, everybody. I hope you have a wonderful day, and good luck on any sort of things that you have to do.
Thank you. Anyone else?